Hello engineers, ladies and gentlemen. Welcome to another tutorial. My name is Delay from DevOps and Cut. Today we shall be doing some more Terraform with this infrastructure as code. But today we shall be adopting some serverless technology. We shall be using Fargate as our compute power rather than EC2, Elastic Compute Cloud. So we're going to deploy with Terraform. We're going to deploy our web page as a container in an ECS cluster, Elastic Container Service. We shall use Terraform to build our VPC, the networking. We shall build two public subnets, two private subnets, target groups, a load balancer. We shall create an ECS cluster. We have a task definition, which will pull our image from Docker Hub. We have our tasks. We have a service for our tasks, and then we shall point our load balancer. We shall put a load balancer in front of a service. So sit back, relax, and let's start. I'll see you at the terminal. Thank you. So what's our plan for today? So our plan is to deploy a web application as a container in an ECS cluster. So what are the prerequisites for this? First thing is you're required to have your remote backend already set up, which is used to store our state files, our Terraform state files created in the AWS account. So therefore, I have done that already. We're using S3 buckets with the DynamoDB backend. So we've named the S3 bucket DevOps on Cut remote backend, and then named the DynamoDB table DevOps on Cut Terraform login. So this has already been set up on the backend. So this will be referenced in our Terraform provider file, making the provider block. Okay. Also, you need to have a Docker image of your application. I've already done mine, and it's already residing in Docker Hub. Okay. Then after that, we're going to begin to create architecture. Okay. So we shall create a VPC. We shall create two public subnets into availability zones. We shall create two private subnets also into availability zones. We shall create a load balancer which is public facing. The public subnet and application will reside in an ECS cluster in the private subnet for security. We shall create an internet gateway for our public subnet and a NAT gateway for our private subnets. The NAT gateway will reside in the public subnet, but it will be created for the private subnet. I hope you understand this, how networking works in AWS. Then we shall create the route tables, routes, and associations for all this. After this, we shall create a load balancer, the listener, and target groups. So this listener will forward HTTP traffic from the load balancer on port 80 from the internet to our target group. Okay, so that's the second step, the load balancer target group, and with the listener. The third, we shall go on. Let me just finish this. Yeah. So the listener will forward HTTP traffic on port 80 coming from the load balancer to the target group. Step 3, we shall create our ECS cluster, a task definition, and we shall create a service to launch our tasks. And then step 4, finally, we shall access application using the load balancer's DNS name. We shall output this when we run Terraform so that we can copy it and view our application from the internet browser. So that's it for the plan. So let's begin to create and write our code. Okay, so the next thing now is to set up our provider, our AWS provider. So let's create the file for this. We can call it provider.tf. It can be any name you prefer. I like to be descriptive. So touch, which is okay. Let's make a directory and put all our Terraform files in the directory. So let's call Terraform. It can be any name of your choice. Okay, and then let's change directory into this Terraform folder and begin building our Terraform code. Terraform. Yes, that's the. So now we can create the first one for the provider. So touch, which is the command to create a file. Touch provider.tf, that's the file. Okay. In this, we shall declare our provider AWS, our version, and also our backend, which we have already created. Remember, that's the backend there. Again, that's our provider and the Terraform block for the Terraform version. We shall have a variables file, so we shall declare our variable type in those files, and then we shall have a terraform.tf vars file. In the tf vars file, we shall now define the values in the file. Okay, so we have a variable called region that will go to our variables file. Yes, so variables.tf. But all we should do here is just declare the type. We shall not hard code anything there. The values will be set in the terraform.tf vars later. Okay, so that's the only variable in our provider. So let's go there. A variable called region, and the type will be a string. It's US61, it's a string, but it will be set in the terraform.tf vars later, so that we can reuse the code without having to go into any of our Terraform main files. Just have a clean code, best practice. Okay. So so we have our provider setup, Terraform version, and our backend, which is the S3 buckets. It's fine. Okay. So after this, we can go and set up our networking. That's fine. Okay, so let's begin with the networking. We should create touch networking.tf. This will host our networking setup, which will be our VPC, the subnets, the route tables, and the gateways. So that's networking.tf. Yes. So let's go in there. First thing we should do is we need a data source to get our zones, our offensive zones, because we shall retrieve it dynamically. So we use a data source to get this from AWS, because we're in US East 1. So it will retrieve the names of the. Yeah, there it is. Yeah. So the data source will retrieve the offensive zones, the available ones, from what we declared in the provider, which will be in US East 1. To return that, and then we can go through its index to dynamically retrieve the values. Okay. So next we declare our VPC. You can see there, and then also the VPC CIDR. The CIDR block is a variable which we shall set. It's going to be a string which we shall set in our tf vars file. So we shall declare it in the variables.tf as a string, and then we'll set the value in terraform.tf vars later. So variable, that's going to be variable of type VPC CIDR is the name, VPC CIDR, and the type will be a string again. To return a string, you just store a string. The value will be 10.0.0.0./16, but we shall set that later. Okay, so VPC done. They're tagged. We shall go on to create our public subnet. Now we shall use the count meta argument, so we can create an X number of subnets. Use the count meta argument, and we shall loop through its values, and the number we want will be set in our variables in the terraform.tf vars later. So that's a smart way of creating an X number of resources. Okay, so let's put in the public subnet. there, you can see the counts is a variable called subnet counts. This will be declared. It will also be it will be a number, type number, and it will create how many we look through the value of counts, and to differentiate between, we've used the count in the index of the count. Yes, you can see there. If we use the first one to create a CIDR block for the subnet. Yes, and also it will retrieve the zones based on the index, so that each one will have a different zone, and at the same time, the tag, the name, will also differ. It will be appended by the index of the count value. So that's so that way we can create for this we shall create just 2 public subnets, but that will be set in the Terraform.tfvars. In the variables, we'll just declare the type as number. And in our Terraform.tfvars, we shall then hard code it to be 2, which we need. We shall do something similar for the private subnet too, because we want 2 of that too in 2 different availability zones. Type string, okay. Okay, so next we shall create for the public subnet, the internet gateway. We shall create the route table, and then the route table association for the public subnet. It needs the internet, so we're going to the internet gateway and the route table. Yes. So that's the code for that. We're going to have 2 route table. We have 2 subnets. So we should use the index of the count function to differentiate between both subnets, and then we shall associate them with the internet gateway. Okay. Yes. So that's the route table. Below there is the route table. That's the routes, and then below that is the route table association. So the subnet ID, we have used the counts, an index of the counts to differentiate between both subnets. Remember, they were created dynamically using have an index, so that will just specify which is which. Okay, so that's the public subnet done. We need to go and create the private subnets. For this, we shall need a NAT gateway, and the NAT gateway will need an elastic IP to be created. Next, we shall go for a NAT gateway, which we create for the private subnets. So that's the NAT gateway code, okay, and the allocation ID will be the elastic IP ID. So we create a subnet, the private subnet there. We're using the count function the same way with the same value. It will be set, and then it will create a subnet. So also create a CIDR block from the VPC CIDR, and then it will name the subnets, both subnets, based on the index, the count from the count meta argument count function. Okay, so then we shall create the NAT gateway. Below there, I can see NAT gateway needs an elastic IP, so we should create an elastic IP as well. That's elastic IP there, AWS EIP. So that's and then next we shall create the route table and association for the private subnets. So that's the NAT gateway. The private subnet there, everything's fine. With the public, the VPC. Let's go back down and let's finish off with the private subnet. So let's create the routes. for the private now, not the public, the private. Okay, so let's go back down. You see, we've named this the private based on the count index to differentiate both. That's the elastic IP for the NAT gateway's allocation ID. Yes. And now let's create the route table, the routes, and then associate that with the private subnets. Once again, trying to show you this properly. You can see the elastic IP. I can see the allocation ID, and the NAT gateway is the ID of the elastic IP. Very vital, or else the application will not work because it wouldn't have access to the internet without having the NAT gateway working properly. Can you see the NAT gateway created in the can you see the subnet ID in the public subnets? But it's going to be associated with the private subnets. Understand this concept. We create a NAT gateway in the public, but it's for the private. To allow the private reach the internet. Yes. So the NAT gateway, you see that, is created in the public subnet, but used by the private subnet. So it's basically extending internet reachability to the private subnet. So next we should create a route table, a private route table in our VPC. We call it the private route table, and then we shall go on to create the routes. You can see the gateway ID is that of our NAT gateway. Yes, correct. And then we shall create an association whereby we shall associate our subnet with our private route table. Okay. Now that's all for the networking parts, the main networking parts. So let's go on to create our security groups. So next we shall create our security groups. Let's create a file called security.tf, and we create two security groups. One for our load balancer, allow HTTP traffic in port 80, that's internet facing, and then we shall create one for our ECS tasks, and that will be also, and that we shall allow incoming traffic from the load balancer security group. Okay, only from the load balancer security group. Port 80 as well. Okay, so let's say that's the one for the load balancer. Yes, so ingress will allow port 80 TCP from anywhere that's internet facing, and that is fine. That's just what we need. Egress there -1 0 for allow downloads. Now for the ECS task, you can see now we're allowing inbound access only from the load balancer. So we're allowing the security group, you can see, is the load balancer security group. So that way, traffic will only be allowed into it from the load balancer. So now we create a load balancer for our application. Let's do touch load balancer.tf. Can be any name. I like to use them that are quite descriptive. That's my choice. Touch the load balancer.tf. Now we shall create an application load balancer, our listener, and our target group. There it is. So let's go into the load balancer and put in the code for that. Let's just go to load balancer.tf. Let's go to that. Hold on, please. Let me load balancer, and let's grab that code we had already in there. Okay. So the first resource is the load balancer. You can see there. And then you can see Loadbalancer, as I said earlier, it will be the public subnet, internet facing. And then we've used the star, because the index, to retrieve the subnet, the right subnet, right? Because there are two subnets, remember, that we're loop through using the count function, count and meta argument. So its type is application. You know, the security group is the one we created earlier. You can see so that's the load balancer done. Now we have the listener. Our listener is for, we allow HTTP traffic, port 80. You're going to listen for that, and then it's going to forward that traffic once it receives it. Okay, so let's go to the listener below. You can see the default action of the listener, type forward, and then the target group ARN. So it's going to forward. That's HTTP traffic from port 80 from the load balancer to our target group. And then finally, we shall create the target group. That's target group below. You can see. So also port 80 HTTP. We've called it ECS Fargate target group because it will do that. The type, remember, the target type is IP. With an IP address, so it will be IP, and that's all for our load balancer setup. So once this is done, we can go on. We need to create our roles. Actually, we need to create roles for our cluster as well. So we need to create a cluster, we need to create roles, we need to create our service and tasks, and the task definition. Okay, so that's looking okay. So let's go on, proceed with the next resource. Next, we're going to create an output. We want to output the load balancer's DNS name when we run our Terraform. So we're going to create an output file, output.tf. That's the name I give it. And then in this, we shall create an output which will be whose value will be the load balancer's DNS name. Yeah. So let's create the output in output.tf. You can see the value is the load balancer's DNS name. It will return that when Terraform runs, and it will output this to our terminal. This we shall now copy, go to the browser, and we can be able to view our website. Remember, the load balancer is going to be connected to application through the service. Okay. So that's that. Let's save it, and let's go and now create a roles for our cluster and everything else. Okay, next, creating a role for access. Let's create a new file. We call it role.tf or imroles.tf. Yeah, imrole.tf. You know what IAM means? Services identity and access management in database. IAM role. So let's create this. We shall use our data source to retrieve the policy, and then for assume role. Yes, assume role is ECS tasks. Yeah, and then when we retrieve that, we shall create our role and then attach our policy to the role. So that's the IAM role. The IAM role created there. You can see the assume role policy is the one we assumed. That's from the data source. So it's now, and then we now get the policy ARN itself, the one for the Amazon ECS task execution. That policy will now be attached to this role. That will allow our tasks to be able to run successfully. Yes. So this is all we need, the permissions we need for our ECS cluster to function properly. Okay, so let's create a cluster now. We'll create another file. Let's go clear this first of all so we can see. Touch cluster.tf, give any name, and let's use cluster because it's descriptive. And then in this, we should create a cluster. So AWS ECS Cluster, yes, and given a name, and we've enabled container insights. Create a cluster. After the cluster, we should go and create a task definition, and then we should create our service. So that's the cluster done. That's a simple cluster, nothing we'll need. So let's go on and create a task. So let's touch task.tf and let us do our task definition. The task definition is where we shall specify our container image. We should grab it from Docker Hub where we've put it, and then we shall be able to create a definition. So there, the definition you can see, network mode, AWS VPC. Yes, it's in VPC. Now we are using Fargate. Remember we said we're going to use Fargate, so we don't have to launch any EC2 instances because we're using Fargate for this. So requires compatibilities. Put Fargate in there. We've declared our CPU and memory. Yeah, there, and then the content definition. You can see image. That is my image there that resides in Docker Hub as the image and the version. Yes, so you can see the pop mappings, everything is there. And that's the task definition. So we shall use a service to run our tasks. It will not be done manually or remotely. A service would launch a task. So that's our task definition done. That's enough for the tasks. We shall go on and create our service now. This service is where we specify how many applications we want to launch, replicas, and also what load balancer we should use, and also, so there you can see, I'll show you this Docker Hub, and there resides our application image, the container image for our web page. So it was created, Docker file, and then pushed to, it was built as an image and pushed to Docker Hub. So our task definition would grab it from there to deploy it when our tasks are run. Okay. So let's go and create a service now. So touch service, so.tf. The service will launch our tasks. That's what the service will, when it starts to launch a task, because it's going to run the definition based on the configuration in the definition. Because it's Fargate, we don't have to provision any EC2s ourselves. AWS will maintain the EC2s in the background for us, so we don't have to worry about management of EC2s. It's serverless. Brilliant. Okay, now you see our service. We've mentioned there it belongs to our cluster. We've stated the task definition, so it knows what to use, the template. If you look, we said app count. The app count is a variable which we shall set. So based on that, we can decide how many we want. Yeah, basically. So you can see the load balancer has been defined there as well, and it depends on arguments. What argument says it depends on the listener. So the listener must be created before the load balancer is created, because it depends on it. Go up, you can see again, our desired count in a variable called app count. So desired count will be the number of the number we need. Okay, so let's go variable. App count, type with number. Remember, in the variables, we're just declaring the types. In Terraform TFVers, we shall declare the exact number of the value of our variables there, all in one place. Okay. So let's clear this. We can begin to prepare our Terraform.tfvers now. Touch Terraform.tfvers, and we shall put in the values for all the variables we have declared from earlier. Yes. So we'll do the region, VPC decider, subnet count, app count, anything else. So let's just go there. Region will be US East 1. Region is equal to US East 1. Now we can declare this. So different teams could use the same configuration and just change for different environments, just change the values in the Terraform.tfvers. VPC decider, we set it as 10.0.0.0/16 with VPC decider. Subnet decider we don't have to set here because that's going to be created dynamically using the count function. Okay. So what else? The subnet count is going to be 2 because we're using it to create 2 of each. So subnet count is equal to 2. Yes. The app count, let's just do 2. We want a replica, so we'll set that as 2 as well. The app count will be 2. So it's now time, let's run Terraform init and let's initialize our configuration. This will download the necessary plugins. It will initiate our backend, remote backend. That is successful. The backend is downloading the plugins from HashiCorp with Terraform version 5. Yes, installing the provider plugins. When this is done, we shall validate our configuration as well, just to make sure that it's syntactically correct. That's a tongue twister. Okay, so it's taking time. I'm going to let this run its course. I wouldn't cut the video and and edit. I wanted you to see how long it is taking to actually initialize. You do the plan, everything else, and the apply. You can actually feel, a real life scenario where it's been done. So let's validate this. It's just going to take the syntax, make sure it's correct. We'll check for minor problems with the alignment, with the brackets and stuff. Okay, that's successful. It's valid. So let's go with the plan. Terraform plan is like a dry run. It will tell us what resources are going to be created. So, remember what I said. Make sure you already have your backend set up for the S3 for your Terraform state files. It has to be set up already before we can do all this. So we've initialized, we've validated. Now let's plan. So that's Terraform plan. The plan might take a few minutes sometimes, depending on the complexity of our configuration. So it's acquiring the state lock. That's in the remote backend. Remember it's locked with DynamoDB. This prevents somebody else from working on the same state file when you're in it. So that was quick. It's going to add 26 resources, 0 to change, 0 to destroy. Okay. So now you can see all that. 26 resources are going to be created when we apply. So next we shall run Terraform apply to actually build our infrastructure, as well as deploy application into the ECS cluster. Okay, so Terraform apply, which I use the auto approve option so that we don't have to wait for it to prompt us for a yes or no. It will just run everything. It will take everything as yes and just run the command. So there'll be no breaks. Okay, so it's now going to plan and then apply. As I said earlier, I will leave this to run its course so you can actually see how long it takes to run this. If you can't wait, you might as well just fast forward this part, But if you want to know what's really going on and how long it takes, just sit down and watch. This is quite a simple, design, so it shouldn't take too long for the application to be completed. Okay, you can see it's building the cluster route tables. I was building the load balancer all being created. You can see the subnet being created, the public subnet up there. That's complete. So it's building all our resources, 26 resources. The roles been done, yes. You can see the NAT gateway still being created. Yes. We're going to create an elastic IP, which will be used by the NAT gateway. So the route table association being created. Yes, you can see the load balancer still being built. The load balancer is still being created. Yes, some resources take a very short time, while some take a much longer time. Yeah. Yes, it's still running. When all this is done, you can see it's finished with the routes. Yes, one of the routes, the public routes has been completed. The NAT gateway has been completed. Yes, do that. So after all this is done, remember we created an output for our load balancer's DNS name in the output.tf. So when this finishes, it will print out the load balancer DNS name to the console, and that we can grab and go to a browser and actually view our deployed application. And we can see our web application which has been deployed onto the ECS cluster, which we have also created. But the load balancer will be in the public subnet interfacing, and then our application, or the cluster, will be in a private subnet. The load balancer will allow port 80 from the internet, and then the application there would only allow, its security group would only allow traffic, but 80 HTTP from the load balancer. Yes, so that's done now, it's completed, and now you can see the load balancer DNS name. We should grab this and go to the browser. Yes, so we'll grab this and go to the browser. Okay, so now let's finally grab our load balancer DNS name and then head on to a browser to view our application. Remember, we did an output.tf where we exported the created load balancer's DNS name in apple.tf. So we should grab that, head down to the browser, yes, and go to our load balancer's DNS address. So let's paste this there, and if all went well, we shall see our web page. The web page was deployed. Oh yes, that is. So it's successful. That's successful. So it's been good. So you have learned how to create infrastructure and then deploy a web application as a container in an ECS cluster. Don't forget to subscribe to my channel, like and share for another interesting tutorial. Daily DevOps Uncut. Thank you.